or not, or self-reflect. Okay, so the top hat question asks you, that you are at 450 degrees Celsius and the composition is 50 weight % antimony in this bismuth antimony isomorphous system. And it asks you what is the weight fraction of the solid phase. Okay, you have several options. Okay, looks like we're just about there. Most of you have all arrived by now, so the last 3 people, get your answers in, please, and we'll move on. All right, I'm going to close in about 3, 2, 1. Okay, so let's look at your answers. Okay, so we have actually quite a bit of Y distribution. So we should definitely go over this problem. Not that we wouldn't anyway, but let's talk about it. So clearly the answer is C. Okay, the phase weight fraction is 0.55. So let's go over that. How would one get to this answer? Okay. So here we are. So what the question is asking for is the weight fraction of the solid phase. So when you're reading an isomorphous phase diagram like this, right, we've identified what the liquid phase region is, what the solid region is. So here it's called alpha, but it could be any Greek letter. Okay, and we want to know the weight fraction. So we need to know where we are on the phase diagram. And so we're here in this red dot. You're at 50 weight %. You read that off of the x-axis. You need to know the second information to know where you are on the plot, right? You need to know the temperature. The question tells you that you're at 450 degrees Celsius. So here you draw your tie line. Let's not zoom in. So if you draw your tie line here, where do you meet C alpha? And where do you meet your CL, which is where it touches the liquidus line. So this line right here is the liquidus. This bottom line is the solidus. Okay. So then you just read off your concentrations, okay, your composition. So then you simply go down and read off of the x-axis your C naught, or sorry, your C alpha. This is your C naught, which is the composition of the system. This is 50 weight% antimony, right? In your entire system, you're given a chunk of something. It has 50 weight% antimony in this alloy. So then where does it touch the liquidus? Right here. You go down, you read what Cl is. So you're just reading Cl and C alpha off of the plot itself. There's no computing. And then when you plug C naught, which is 50, Cl is 32. So here's the 30 mark. C alpha is 65. I'll write this out explicitly. So then when you calculate the weight fraction or the mass fraction of the solid phase or the alpha phase, you get this. Now, if it were an open-ended question where you're supposed to provide the answer, you would provide such a number. If it were multiple choice, your life gets a little bit easier because look at the Tieline, okay? Look at this line right here. Where your C naught is, where is it in that line? It looks like about half, right? If you just had to eyeball it, it looks like about half of the line is on your left and half of the line is on your right. So if it were multiple choice, you can rule out most of the options without doing the calculation itself. Any questions about this particular methodology? So then the reciprocal question could be, what is the phase weight fraction of the liquid phase at this particular composition and temperature? So how would you approach that? Yes? So the answer from the back is 1 minus the phase weight fraction or the phase mass fraction of the solid phase, because you only have 2 phases as you've identified in this particular phase field. So it's just 1 minus that. If you had to compute it just to do a sanity check to make sure, because what if you did W alpha incorrectly, okay? Well, then you can just calculate the fraction of liquid by doing C alpha minus C naught divided by C alpha, the entire line, C alpha minus CL. Okay, so you just take the fraction, which should get you 0.45. Okay? So 2 ways. What your colleague said, just 1 minus that. Save yourself some time if you're pretty confident with your C alpha, W alpha calculation, or you do a sanity check and just chug it out. Okay? Just crunch the numbers. Okay, this is the start of it all, okay? So I hope we're all in sync before we go on, because there's just going to be more of this as we go on with eutectic phase diagrams and eutectoid phase diagrams, okay? It's going to be more lever rule implementation as well as reading off of the phase diagram. So get your questions out now before we continue. Any other questions? Okay. By silence, I'm going to accept it as that everybody has agreed and we're on the same page. Okay. Now, next step. So you have nickel and copper. Everything is simpatico. Hume-Rothery rules are satisfied. You have solid solubility throughout the entire composition. What happens when you have limited solubility, right? Not everything in the world is going to be, is going to mix well with each other. They're not going to satisfy the Hume-Rothery rules. So if you have limited solid solubility, we'll talk about a particular case where you have a eutectic point and why that is advantageous for when you're making alloys. Okay, so here's an example, the copper-silver system. You also have the animated version of this phase diagram in Wiley Plus, and in fact, your homework asks you to refer to this phase diagram as you move along in composition as well as in temperature. And so what this eutectic point or this eutectic binary phase diagram tells you is that you can go from a liquid, so that's L again, and instead of just going to one phase in the solid form, you can actually get two phases, particularly right at this point right here, when you go down in temperature, and you hit what's called the eutectic temperature. For this particular system, it's about 779 degrees Celsius. And right at the composition CE, or 71.9 weight percent of silver in a copper-silver alloy system, you have the liquid going to a solid phase alpha and a solid phase beta. This is particularly special because you see the melting point of copper is up here, right, somewhere between 1,000 and 1,200 degrees Celsius. And then you see the silver melting point. But at this particular composition of 71.9 weight percent silver in this alloy, you see a depression in the phase transformation temperature, right? Instead of 1,200 or 900, the transition temperature is actually 779. So you depress the melting point, right? So it's now at a more, it's a more usable temperature, slightly. I mean, it's lower. This is more particular when you have things like lead, tin, solder, okay? And your melting temperature can get down to as low as 183 degrees Celsius, which is great because the lower the melting point, right, the less heat you have to apply to melt your solder. So it's more advantageous in terms of manufacturing and commercial use. What's also special about this eutectic point is that three phases can coexist. You have liquid, you have alpha solid, and you have beta solid. Okay. What's also particular about this composition is the microstructure that we'll talk about in today's lecture and tomorrow's lecture, although we'll be talking, the next lecture we'll be talking about eutectoid microstructure. But basically, this composition will lead to a striped kind of microstructure, which will then, of course, affect the strength of your material, so it affects mechanical properties. Right? It introduces grain boundaries that can help impede dislocation, which will strengthen your material. Okay. So what exactly is alpha and beta? Right? We said it's solid, right? So it's a phase, and there's some limited solubility. And so here we see things that we've seen before with the isomorphous binary phase diagram. We see things such as this line. We call that still the liquidus line. Right, so above the liquidus line, everything is liquid. You have everything in the liquid state. Below the solidus line, you have everything in the solid form, and that's this line right here. All right, so that's your solidus, and there's a solidus line right here over as well. And then you have an introduction of this line right here, the separation between a single phase area and a two-phase region. So this new line that's on the left as well as on the right is your solvus. Oh, let me be a little bit more clear. Okay, that's your solvus. It separates the one phase and the two phase solid region. And so what this is telling us is there's limited solubility. If you can see here, if you're trying to put silver into copper, you'd have to be at like 800 C or so for some substantial amount of silver to start going into the system. And in fact, the maximum solubility of silver into copper for the alpha phase is right here, is 8 weight %. That means if you're at 800 C, you can put in a maximum of 8 weight % silver into copper matrix before you get a two-phase region. You can just keep on putting it into the alpha. So alpha in this case is the parent phase of copper. And copper we know is FCC. So if you have a matrix, a copper matrix that's FCC, and you start to substitute in, silver, it will still maintain FCC at 800 C up until you hit 8 weight %. And then interesting things start to happen. Okay? So we'll talk about that. And then, of course, here, if you're in the silver region, you're in the beta phase, now you have silver matrix and you're trying to put in copper. There's also limited solubility. In fact, it's under 9%. Okay, so that's what I mean by limited solubility. And if you're at room temperature, actually this goes down to 200 degrees Celsius. If you're at room temperature, forget it. There's no solubility according to the phase diagram. Because look, already at 400, how much silver can you put into copper? I mean, you really have to zoom in. Maybe you can put in point something, 0.000 something, but it's extremely difficult because there's limited solubility. That's what the phase diagram is telling us. Okay, so if you want copper and you're trying to strengthen copper with silver, you can, but you have to elevate the temperature to 800, and then you can get the silver in there with some limited solubility. And then you just get alpha and beta. You get a two-phase system, and then your microstructure is different, your properties are different. You have a whole different beast. Okay? So that's how one would read this phase diagram. You need to recognize the important, where is the eutectic point? And it's important enough that most phase diagrams will just point out to you what the composition of the system is when you're at the eutectic concentration. Okay, 71.9 weight % silver in this particular case. Now, if you've done some of the homework, maybe you've also seen that there's a lead tin system. Now, it's the classic eutectic system because it's simple, relatively simple like this. It has well-defined regions, and of course, it has wide commercial applications, and thus we use it for teaching purposes. Okay. So let me erase some of these marking just so I can be a little bit more clear. Although this is still wrong, it's still silver. So let's look at the two-phase regions, right? You have multiple of them. Here you have liquid, but any composition from here to here, your solubility limit of silver going into copper is what's called the hypo, so less than or below, you're less than the eutectic concentration or eutectic composition. So that's hypo. Above that is hyper. Okay, so I'll just write that out explicitly. Hypo, hyper. So this is a eutectic system. So it's hypo-eutectic and hyper-eutectic. So below 779 C, in both hypo and hyper, you have two-phase alpha and beta. Above that, above 779 degrees Celsius, you still could have two-phase regions if you're in this area right here, in this phase field, and in this phase field right here. In this region, you have liquid and alpha. solid, right? So reminiscent of isomorphous, binary, right? You're coming down from the liquid, you hit the liquidus, and then you enter a two-phase liquid and solid region. Here we call it alpha because it's next to the alpha phase. And then if you're in the hyper region, you start in the green liquid area, and then you hit the liquidus line, and your material will then start forming this beta phase. Okay, so you form this beta phase right here, and we call that beta phase to distinguish it from this beta phase. So above and below, we have two terms to distinguish what kind of beta or what kind of alpha we're talking about. Above 779 C, which is above the eutectic temperature for this phase diagram, we call that ProEutectic alpha or primary alpha. And then below that, the alpha that you form is going to be eutectic alpha or eutectic beta, right? So by just delineating our terminology, we've communicated to somebody else what temperature range we're at and what we're talking about. Okay, we're also communicating the microstructure of the material just based on the terminology itself. Okay, questions? Yes?
When you say that like it's soluble,
Mm-hmm.
does that mean like we're like decap, like if you were to zoom in like decap that you have like interstitial versus substitutional?
Yeah, well, the interstitial, so the question is, what do I mean by solubility? Am I distinguishing between substitutional versus interstitial placement? That depends on the relative atomic radius of the system. So in the eutectoid case that we'll talk about in a little bit at the end of this lecture or the beginning of next lecture, we're talking about putting carbon into iron, right? So the previous example that we saw, carbon can fit into the BCC and the FCC interstitials of iron. So there, that would be an interstitial case. Here, it would be a substitutional case. There is a chance, because of statistics, there is a chance that silver could go onto an interstitial site. That is highly unlikely because, as we've seen, when you put a larger atom into a small site, it's possible, but energetically unfavorable. Okay, so it's highly unlikely to happen. Could you find one randomly if you were to pick up a chunk of copper silver? Absolutely. Statistically speaking, anything is possible. But in the case of all these standard conditions, it is extremely highly unlikely. Now, to get at your point more generally, as opposed to these two specific cases, you just have to look at the atomic radius and see, will it fit into the crystal site that I'm talking about? So the parent phase, in this case, if I'm over here in this region, the parent phase is alpha. So if I'm trying to fit another atom into alpha, which is here, copper FCC, I have to think about, okay, how big is copper? How big is that FCC site? And my second atom, if I'm putting it there, can I do it? And is it close in atomic radius? So those are the general rules I would be looking to when I try to answer that question in the real world. Question?
You said that alpha region is called what?
It's just a two-phase region. I didn't call it anything in particular for this area, but this region, are you talking about this region in general in terms of composition, or just that little wedge? Oh, ProEutectic. Okay. So the question was, is there a specific name for this area? There is in the sense that the alpha that comes out. So how do you distinguish what alpha you're talking about, right? So here, if you're in this particular region, so this composition, the maximum solubility of silver into copper for the one phase region, all the way to the eutectic composition, if you're coming down and melting, solidifying, I guess you could also go up either way, but if you're changing the temperature within that composition, the alpha that you form in this wedge right here that is called the alpha is called ProEutectic Alpha or primary alpha. They're synonymous. That's it. Okay. So next we'll talk about a particular system here. We'll read off of the plot. I've also sent out your supplemental slides because I thought you need more writing room. So I figured I'd upload something where we can write together and that you're not trying to find space on, you know, the edges of these slides. So let me just jump to that because that will highlight this better. So this was the supplement. So you're going to have to switch a little bit, but it will help you. If not, you can also keep on going with the current slide deck because they are the same phase diagrams. I've just rearranged it so that there's just more writing room. Okay. Okay. So let's talk about the microstructure and why this matters to you as an engineer. Okay, this is the same phase diagram that I just showed. Specifically, I'm going to do an example in the hypoeutectic region. In this particular case, you have 40 weight% tin, and you're at 150 degrees Celsius. Okay, so let's mark that. That's 40 weight% tin and 150 degrees Celsius. That puts you right there where the red dot is. Okay, so you can mark whichever slide deck you want or copy down this, phase diagram. So if you're here and you're in the liquid, right, what does that microstructure look like? If you remember from isomorphous binary phase diagram, you just have an entire blob. So if you're looking through some microscope, you know, it just looks like some blob. It's all liquid, right? As you cool down, okay, you enter this, what is this? Let's call this alpha, let's call this beta. So then you enter in a liquid and solid region. Okay. So what does that look like in terms of the isomorphous binary example? It looks like you start to see solidification of the alpha phase, right? Alpha is coming out. You're solidifying your system. So then the microstructure looks something like this, where you now, instead of liquid, in fact, I'm going to delete this and just make liquid white so I don't have to color as much. Okay. So then you start have alpha coming out, these little solids, and they're going to grow, right, based on the calculations of our phase weight fraction and also the rules of solidification. So this is now your primary alpha. So we'll call that primary or pro. Okay. So we're calling these blobs the primary alpha, ProEutectic Alpha. Okay. And then below 183 degrees Celsius, I'm going to erase that just so you can see it a little bit better. Below that, you're going to have a different crystal structure, or sorry, microstructure. So here is you're in this alpha plus beta region. You get what looks like, you still have your solidified alpha. And in fact, they've grown a little bit, so let's make them a little bit bigger. You know, let's say they've grown a little bit as you decrease in temperature. And then the rest, after 183 degrees Celsius, everything becomes solid. And you have alpha and beta. But what does the rest look like? The rest looks like these stripes, or lamellae, or lattice. All terms that refer to the same thing. Okay? They all refer to this striped-like microstructure. And so you have your primary alpha still, and you have now your eutectic alpha interspersed with eutectic beta. Okay. So why does the stripe form? The stripe forms because as soon as you're at 184th degree C, then you're at 183, and then all of a sudden you're at, let's say, 182. This happens relatively fast, right? So at one point you're above, and at one point you're right below the eutectic temperature. And when that happens, when you go from some liquid now to all solid, you're going to be diffusion limited, right? All these atoms, these tin atoms, 40 weight% of tin has to go somewhere. And the balance of lead also has to go somewhere. So what happens is the tin atoms will start diffusing, okay? They'll start diffusing, and the path of diffusion, what happens in these microstructures is they form these stripes, because the tin will go into the beta regions, and then you'll have the alpha region and the beta region. So alpha has lead and tin, and beta also has lead and tin. Okay. Let's talk about the hold that thought. I'll come right back. Let's talk about the microstructure of the eutectic composition. What happens when you're coming down in temperature, so you're solidifying right at 61.9 weight% tin in this lead tin system. Okay, so the microstructure will look something like this, where you have liquid, just like this. And then you just go from liquid to alpha plus beta. So right at the eutectic composition, CE, you go from liquid to alpha plus beta, right? 183, and then 182, you have alpha and beta. So then your microstructure below the eutectic temperature, okay, so below eutectic temperature, your microstructure just looks like these stripes. And they don't actually, they actually look like this. The stripes look, the grains are not oriented in the same way. They could be randomized, whatever it is, however they solidify isotropically. Question and then question. Yes? I answered it. Yes?
In your drawing, when you wrote the third circle down, like the alpha plus beta,
Mm-hmm.
yeah, is that where that dot exists on
Yes.
the diagram?
Mm-hmm.
And then the one above that, the liquid to L plus alpha, is that transition arrow right there? Okay.
Well, this is anywhere, right? If it's above the liquid, it is liquid through and through. Question?
So if we were starting on the
Mm-hmm.
the
Yeah.
stripes form first now?
I didn't hear the second part. Will what form first?
The stripes.
No. So yeah, let me clarify that. So let me erase a little bit, not only in part, because I know some of you are still writing this down, but let me actually change just the color so I can be a little bit more clear. Okay, so the question is, what if I'm in this region and I force it to go through beta? So let's say I'm in some extreme composition, let's say 99 weight% of tin, okay? That forces me to go from here, 99 is here, that's atomic percent, so 99 is here, yeah. So I go through beta. So here I'm in the liquid phase. So blue is now the microstructure for 99 weight% tin. So I have liquid, and then I enter, well, that depends. If you're 99 and you go through beta, but you don't go through L plus beta, it looks something like this. If you have just beta, these are all solid. Okay. No. Okay. Whew. So it's all beta. Okay. Those are the lines that I drew are grains of beta. So it's all solid beta, and those are just grain boundaries. And then, let's say if you're not 99, you just keep on having beta. That's it. Analogously, okay, now I have to pick a different color. I think we have green left. Let's pick a green. Let's say you go from here to here. All right, so I'm going to go in this region. I'm going to demarcate this region right here up until, okay, so this, I'm going to talk about this range of composition. If I start from here, it's liquid, and then I go into a two-phase L plus alpha region right here, okay? So it looks something like this. And then I solidify and go into an all-solid alpha region. So then it would look something like this, where I just have grains of alpha. Okay, so it's all solid alpha at this point. And let's say I keep on going down. Now some beta has to form, but not that much. So what does it look like? It could, so I still have alpha grains, all solid. So then the beta could show up as some precipitate like this. Depending on your material, it could be in the grain like this, and it could also be right at the grain boundaries like this. That's what the microstructure would look like when you solidify in this composition range for this eutectic phase diagram. I'll follow up analogously. Let's go to the solubility limit. I'm going to erase. Is it okay if I erase, or is there going to be like outcry? I'm going to erase the green part. Okay, no outcry. Okay, since I'm on purple, I'm going to stick with purple. Let's talk about this region right here, right, where you have limited solubility. Let's say I start here, because here you'll still kind of go through the liquid plus alpha, then you come down and you have alpha, and then you keep going down and you just stay in alpha. You never see beta in that region, okay? Do you see that? I'm going to go over it one more. Liquid, tiniest bit of alpha coming through, and then just more alpha. So the final microstructure looks something like this. This is alpha, alpha, alpha. You know, these are just grain boundaries, alpha, alpha. So it's just all solid, no beta precipitates. Yes, question? Yes. If we go through liquid plus beta, is it analogous to liquid plus alpha? The answer is yes. So I'm going to erase. I'm running out of color, so I'm going to stick to purple. But the question is, if I'm in this region, I get, I get liquid plus beta, but beta specifically is ProEutectic beta or primary beta. So analogously, you could write liquid plus beta in the hyper-eutectic region. And then you solidify and you get these stripes. And so you get something similar, except now instead of primary alpha, this now becomes primary beta. Microstructure is analogous, different names. Yes?
So are the stripes the grain boundaries?
The stripes are the grain boundaries, but they also represent, let me go back to the red. They're actually thick regions. They're not just grain boundaries. Yes, there are grain boundaries because let's say the white region has to interface. Well, if I said white is liquid, now I have to change to a different color. If beta is purple in this case, so it looks something like this. So yeah, you do have a grain boundary right here in between the two stripes, or the two laths, or the two lamellae. All different names, same thing. Okay, and it looks something like this. And since I'm doing the liquid plus beta example, this should be primary beta if beta is purple. Okay, yeah. Mm-hmm. In the hyper section, is there a primary? Oh wait. Oh, this right here. No. Well, okay, because your blobs just become grains, right? You don't have to distinguish between primary and eutectic because there is none. Right? The eutectic is denoting that microstructure that's like that. And so here in this example, to clarify, if you just have these blobs that grow and grow as you solidify, they, you know, the solid chunks just get bigger and bigger, then you just have a bunch of alpha, right? You don't have the eutectic part. Okay, last question before I crunch some numbers. Yes? Yes. Do I need to repeat that? Okay. Okay, so the question is, what does a microstructure look like? It looks something like this. So below, well, 150, so you're right here. Let's go back. So it looks exactly like this right here, right? Where you have primary, alpha, and then you have, oops, and that would be complete. Now, let's crunch some numbers. Okay, now we understand the microstructure. We need to know what exactly are the mass fractions or the phase weight fraction. So how can we determine that? Well, we can use the lever rule and draw our tie line. So if we're right there, let's go back and draw our tie line. I'm going to clear this up just a little bit. Oh, oh my. Okay, so let's draw our tie line. You're here. Let's draw the tie line. Okay. That's our tie line. So our C naught is 40 weight percent. C beta, eyeballing it, is 99. And then C, we read this off, this is alpha. So C alpha is 11. So what I'm going to do is just transfer some of these numbers onto the next slide. Okay, so we said C naught is 40, C alpha is 11 weight percent tin, and C beta we read off of the plot as 99 weight percent tin. So then if we put in C beta is 99, C naught is 40, that's the composition of our system. C beta is 99 minus 11. So what is it that we're doing graphically? C beta is right here. Whoa. Okay, it does not seem to want to register. So the phase fraction, what we're doing for calculating the phase fraction of alpha is we're dividing this segment by the entire segment, by the entire length. That's all we're doing. Okay, we're implementing the lever rule like we did for isomorphous binary phase diagram to now eutectic. Okay, so that's what we just did graphically. We're going to crunch that number out, and we get 59 over 88, which is, so that's the fraction of alpha that you have. Analogously, so beta, the mass fraction would be 0.33, 1 minus W alpha. You could also calculate these numbers so that you check your calculations. Okay. So that's total alpha, right? I have not distinguished between primary alpha and eutectic alpha. All I've asked is, how much alpha do you have right at that point? And how much beta do you have I haven't asked about the micro constituents, which means I haven't asked you to delineate what is primary and what is eutectic. That's the next section. So the next section says, what is the phase weight fraction or mass fraction of primary alpha and the eutectic microconstituents? So all these terms that we've been discussing, primary, eutectic alpha, eutectic beta, those are microconstituents that make up your microstructure. So we can now delineate how much of alpha total that exists in your system is primary and how much of it is the eutectic alpha. So I'm going to go back to the plot, and I know if I'm coming down to this liquid plus alpha region, I'm going to form out primary alpha first. I'm going to form ProEutectic Alpha first, right? That's what I hit in terms of the temperature when I'm solidifying. Then I know after I pass this temperature right here, all that remains in the liquid, so I have solidified alpha at this point, okay? That's your primary. All the remaining liquid has to separate into eutectic alpha and eutectic beta. So I want to know, before I hit that eutectic temperature, how much primary alpha did I have, right? So I can do that. I can just look at the lever rule right here. I say if I'm right here, if this is my composition right here, I can compute that lever rule and I can tell you how much liquid I have and how much primary alpha I have. Okay, so now we're going to get to how much of these blobs, how much of these primary alphas do I form first. So that's what the next equation is for. So the lever rule, I know my eutectic composition is 61.9 weight percent tin, and I know that because I read it off of the plot. I read it off of the diagram. My composition in the entire system is 40 weight percent, still hasn't changed. And then the entire length is C eutectic is 61.9 and C alpha at the eutectic temperature is 18.3. Where did I get that? Off of the phase diagram. I'm going to go back to the plot. If I draw my Tieline, okay, CE right here, if I come down, well, it's already drawn for you. 61.9, and then the next where it hits the solid is 18.3, but you can also read that off of here, although probably not because it's really detailed for this kind of rendering. But it's already written for you, so I'm just reading these compositions off of the diagram. I'm not computing anything yet. What I am computing is the phase fraction of the primary alpha. And so if I compute these numbers, I get all right, so what this is telling me is I have, as I'm coming down in temperature at composition of 40 weight percent tin, I have 50% or 0.502 fraction in primary alpha. That means the remaining, the balance is all liquid. Now all of that liquid is going to come out as two eutectics, okay? So all that liquid, so the W eutectic should come out to be 1 minus W alpha primary. So let's see if that actually works. So we have 40 for C naught minus C alpha at eutectic is 18.3. The entire length does not change, and I get 21.7 divided by 43.6 equals 0.498. So that adds up to 1 because all of the eutectic came from the liquid, right? It comes down, some of it comes out as solidified primary alpha. The remaining liquid right after eutectic temperature is going to give you eutectic alpha and eutectic beta. Okay, now you've accounted for almost all of the microconstituents, right? You have primary alpha, check. You have eutectic beta, check. What don't you have left? The third one. Almost. It came from the liquid. No, beta is already here. You don't have primary beta because you're in the hypoeutectic region. You only have primary beta when you're in the hypereutectic region. Okay, so you have primary alpha. You've accounted for that. You just calculated that. After the eutectic transition, you have, well, it deleted it, but you have eutectic beta and eutectic alpha. That's what we haven't explicitly written out. So we can do that. We can compute that, right? So whatever remains, you have primary alpha. You've just calculated for that. You've already calculated what the total is. So let's get those numbers. So W alpha is 0.67. And you've just computed what W alpha primary is, which is 0.502. So the remaining part is the fraction, the mass fraction of the eutectic alpha, and that gives you a very small number. Okay, so all fractions should add up to 1. So you do a check. Okay, so you have primary plus your fraction of alpha in the eutectic plus your fraction of beta, but beta is also in the eutectic. So this we said was 0.502. This we just calculated as 0.168, and this was 0.33 from a previous calculation on the last page, and that all adds up to 1. Okay, so that's all fraction and that's all relative. So if you have a certain mass, let's say you have a 1 kilogram sample, what are the masses of each? Well, I picked a nice number, obviously, for the sake of this example, but you would just multiply it by the mass, right? Your fraction by the mass. So we would have 0.502 of 1 kilogram, so you would have total and consequently and then of course, so I don't belabor the point, yes, question. Is there primary beta? No, because you've never, primary means you're in the pro-eutectic region, right? That means you're above the eutectic temperature. So at 40 weight % tin, when you're coming down and solidifying, you never see beta above the eutectic transition temperature. You only see it after the eutectic transition temperature. And so at 150 C, you're already after that. So the only beta that you'll ever see at that composition and temperature is the eutectic beta, which means it's only in the lads, it's not in the blobs. Okay? It's in the stripes, not in the blob. Any additional question on how to manipulate the lever rule for eutectic diagram? No, you can't. So the question is, if you're at 61.9 weight % tin, would you ever see primary beta? No, right? Because it's going from liquid and it goes straight to eutectic alpha and eutectic beta. It never even sees primary alpha either. All right, I'll see you Friday.